To implement the iterative depth first search solution, I'm going to use a stack to track where we've been. I'm also going to use a list to track what we've already visited. And I'm going to mark the current node with _C as the start node. Then, as long as the current node is not equal to our target node, I'm going to run through an iteration. First, we set our current node equal to visited. Then we get a list of unvisited nodes. Then we get a list of the unvisited neighbors of C. If this list is empty, then we know we can't go any further by following C. So we're going to pop that off of our stack. And then we update our current node to be the next topmost element in the stack. If there are still unvisited neighbors in our current node, then we set our current node equal to one of the unvisited neighbors. I'm just going to say that our unvisited neighbors object is a list, and we get the first element. And then we just push that onto our stack. Eventually, our current node will equal our end node, at which point we'll break out of the loop, and we can return the stack. So that's the iterative implementation of depth first search. It's pretty easy to implement and relatively straightforward. The stack implementation is memory friendly because it only grows to the size of the path. Depth first search does have some drawbacks. Primarily, it could go very deep down the wrong path. Let's take, for example, this maze. We can clearly get to the end in one step if we first choose to go south, but the depth first search algorithm could send us east first, and we'd have to explore the entire maze before finding a solution. If multiple paths exist to a target and we want to find the shortest path, it's better to use something like breadth first search. We'll cover that in the next lecture. So that's depth first search in a nutshell. In this lesson, we converted a maze into a graph. Being able to convert a system into nodes and edges is an important skill. You should always try to represent systems you see in the real world as graphs. Just ask yourself, what are the entities and what are the relationships of this system? We covered recursive depth first search and iterative depth first search. Recursive depth first search is relatively easy to implement, and iterative depth first search is memory friendly. We also saw one of the drawbacks of depth first search, being that we could go very deep in the wrong direction. In the next section, I'll address some of the shortcomings of depth first search using breadth first search.